Okay, let's go over the second handout that was your homework, the laws of planetary motion. I graded that, and I noticed a few errors here and there, but for the most part, you guys are doing pretty well. But let's quickly go over this. This should be an easier worksheet than the other one. So, number one, the diagram below represents a simple geocentric model. What you need to remember is geo, it's like geology, center. Geology is the study of Earth. So in the center, you should have gotten Earth, A, for number one. Number two, which planet has an orbit with an eccentricity most similar to the eccentricity of the Moon's orbit around Earth? So I'm going to go here. First thing I want to see is what is the Moon's eccentricity? And if I take a look at that, the Moon's eccentricity is 0.055. The number that's closest to that is right here, 0.054. So the answer should be Saturn, which is choice D for number two. Number three, which object is located at one foci of the elliptical orbit of Mars? And I think I told you guys this in the video. It's also in your notes. For any planet in our solar system, the focus is something that does not move at all, and we know what sits in the center of our solar system and does not move is the sun. I don't care what planet they're asking you about, Mars, Neptune, Mercury, Earth, if they ask you about what is always one of the foci, it is the sun, choice A. But it won't be choice A all the time. Okay, which diagram shows a planet with the least eccentric orbit? That means that the eccentricity would be closer to zero. And we said zero looks like a circle, so you're looking for the shape that is most circular. That would be choice A. I noticed a lot of people put D for this one. D is the exact opposite. That would be the highest eccentricity. So the correct answer here is A. All right, let's go to number five. Number five, what is the approximate eccentricity of this elliptical orbit? So you would first measure the distance between the two foci, and I don't have a ruler on me, so I'm not sure what that is. Then remember, to find the major axis, you would draw a line right through the two foci from one of the ellipse to the other, so measuring from here to here. And the number that you should have come out to for number five is choice C, 0.7. Earth's orbital velocity is slowest on July 5th. I don't know if you remember, I talked about perihelion and aphelion. Aphelion means A for away, and the closer we are to the sun, the more gravitational pull we have. So therefore, July 5th, we're actually further away. So the correct answer for number six is B. We are furthest from the sun actually in the summer, and that's why we move slower in our orbit. The sun is not pulling at us. Number seven, compared to the terrestrial planets, the Jovian planets have, so you just got to go through the choices here. And if you take a look at choice D, remember the Jovian planets, they are the outer planets. You start with Jupiter, J for Jovian, and look at the, what did we say the answer was here? Longer periods of revolution, right. So if you take a look, here are the Jovian planets. They go for years to do a full revolution. But look at the inner planets, very quick, matter of days. Actually, this is 2 Earth years right here. But either way, the Jovian planets have a longer period of revolution, much longer than the terrestrial planets. So the correct answer for 7 is D. All right, let's wrap it up. Number 8, the diagram below shows 4 positions of a planet in its orbit around the sun. At which position is the planet's orbital speed greatest? Now, by the way, they could just put star here. They could say it's any planet, which they actually do in number 9. But right here, we're talking about some planet orbiting around the sun, and it would be fastest right here when you're closest to the sun. So you should have gotten, for number 8, choice B. And then remember, as we go further from the sun, we slow down until we hit our furthest position from the sun, which, by the way, remember the major axis, the line you drew? That would be our slowest movement, right where the major axis is touching the ellipse. This would be slowest, that would be fastest. All right, number 9. As the planet makes one complete revolution around the star, and this is what I was saying before, this would be like the sun. It could work in any solar system. We call that star in the center of the solar system, for us, the sun, but they could point out that this is any solar system, not even ours. All right, so here we go. As the planet makes one complete revolution around the star, starting at the position shown, what happens to the gravitational attraction? Now remember what I said, the closer we are to the sun, the more gravitational attraction or gravitational pull we have. Now as we start to move, we're going further away. So we're decreasing our gravitational attraction until boom, we hit that major axis, the other point. This is aphelion. Now we're going to start to move closer to the sun. So instead of the gravitational attraction decreasing, which it did up to this point, now it's starting to move closer, it will start to increase. So the correct answer here is choice A. We will decrease until we hit here, then increase. All right, and then lastly, which two characteristics do all Jovian planets have in common? The correct answer is C. You know that because look, here are the Jovian planets. And if you take a look, they have very large diameters, meaning they are tremendous in size, and low densities, right? Look at the density here because they are the gas giants, and gas is a much lower density. All right, hopefully that all helped, and you guys can take a good look at that. And we're going to move on with moon phases on Monday. Hope you're having a good weekend. Stay in, stay healthy, and hopefully we'll see each other again soon. Talk to you soon. Bye-bye.